Hi, and welcome to the Introduction to Fullstack and DevOps Engineering course. I am Nicolas, and I will be your instructor. In this video, I will begin by introducing myself. Then, I will explain the curriculum that we will be following throughout this course. And finally, what you are expected to gain after completing the content. As mentioned, my name is Nicolas Al-Khouri. I am a computer engineer from Lebanon, a very small and beautiful country on the Mediterranean Sea in the Middle East. I have more than 7 years of experience in providing solutions related to DevOps, cloud infrastructure, and software engineering in general. I have worked in several positions as DevOps engineer, software engineer, and solutions architect, as well as leading teams of developers and DevOps engineer. In addition to that, I am a university instructor teaching courses very similar to this one. Academically, I have a Bachelor of Engineering in Computer Engineering and a Master's in Information Systems Security. Moreover, I have 2 publications with very long titles, which you can see in the slides. In addition to my professional career, I am a strong believer in community work. I am one of the founders of the AWS Beirut User Group. We organized and delivered to date dozens of workshops and tutorials related to AWS. I am also a mentor at the Meta Developer Circle Beirut. I delivered several presentations and workshops related to software development and microservices in general. And I am a member of the AWS Community Builders. I created multiple articles related to AWS in general for the global tech community. Currently, I have passed all the AWS Associate Certificates and the Terraform Associate Certificate, and I surely hope to obtain some more. This course is composed of 2 modules, 1, Web Applications, and 2, Infrastructure and Application Deployment. Each module is made of several lectures, each of which is composed of a theoretical part in which I explain certain concepts, and a practical part consisting of exercises and demos to apply the knowledge learned in order to make sense of the information. I will be using Amazon Web Services in my demos, which will give you a great overview of cloud computing in general and AWS in particular. Finally, there will be a section that contains quizzes and a course project to test everything that you have learned. To benefit from this course, I highly recommend that you understand the material, redo the exercises on your own, and finally solve the quizzes and the course project. If you do not have access to an AWS account, the exercises are designed to work on any Linux machine. The topics that will be explained in this course are mostly introductory. First, we will warm up with some of the most needed Linux commands, since we will be using them in all of our exercises. Then, we will familiarize ourselves with web applications, namely what they are and what they are made of. In addition, we will dive deeper into the server side, especially databases and backend services. Afterward, we will explain some of the most important existing infrastructure types. And finally, we will introduce Docker, which is one of the most popular container engines. I created this course since a lot of individuals, especially fresh graduates and junior engineers, are unsure of how to start a career in full stack or DevOps engineering, in addition to the high demand in these 2 fields. Upon completing this course, I expect that you will have a basic understanding of web applications in general, what they are, why we need them, and how they are developed and deployed. Containers and Docker. You should be able to containerize applications and perform basic deployments of containers. Cloud computing in general, and Amazon Web Services in particular. And finally, you should be equipped with the basic concepts of DevOps. In summary, this course aims to teach you the basic information that you need to kickstart a career in full stack or in DevOps. What differentiates this course is that it focuses a lot on understanding concepts and ideas and thought process, which will allow you to further expand this knowledge on your own or hopefully in more advanced courses. So, without further ado, let us begin by introducing DevOps. Hi, and welcome to this lecture entitled DevOps, what it is and what it isn't. DevOps, SysOps, DevSecOps, CloudOps are all catchy and trendy buzzwords that are circulating all over the world and the tech realm. A simple search for such keywords will return thousands of people and companies applying them one way or the other. Unfortunately, as with most trends, numerous definitions and variations arise, confusing the general public, creating irrelevant job positions and career paths, and leading to inefficient software development life cycles, further complicating everything. In this lecture, we try to define what DevOps really is by discussing the evolution of the software industry, some of the most popular software delivery models, and finally, what is DevOps and what are DevOps engineers. A lot of things change in the past years, especially in software-related solutions, which can be summarized in these points. I'm going to read them as they are since they are self-descriptive. Today, almost everything is digitized. Software companies are everywhere. Microservices are now a thing and Kubernetes is everywhere. Cloud providers now have hundreds of managed services as opposed to having a few compute services a few years ago. Continuous delivery tools allow us to easily automate everything. Infrastructure can now be created and managed through code. Multi-cloud solutions are becoming popular. Everyone wants to become a DevOps engineer, and all companies want to apply DevOps. However, one thing did really not change. There is no clear definition of DevOps. DevOps is nothing more than a software delivery model embracing today's available technologies and aiming to enhance the software development lifecycle. To better understand DevOps, it is important to understand the preceding models, namely the waterfall and agile models. The waterfall model is one of the oldest software delivery models, introduced in the 70s, long before I was born. It divides the software development lifecycle into predefined sequential phases, each performing a specific activity and must be fully complete before the next one can begin, with no overlap between them. For example, business analysts must complete all the application requirements and design. The developers will then use the complete documents to develop all of the application. Once done, the QA engineers will fully test the code before being finally deployed by the operations team. With the current technological advancements and capabilities, this model becomes cumbersome and inefficient. In fact, the model employs rigid processes discouraging changes. It is also difficult to measure progress due to the siloed mode of work. And finally, the deployments are slow and complex. The Agile model, formally launched in the early 2000s, provides a more flexible approach to deliver software. Unlike the waterfall model, Agile promotes continuous iteration of design, development, and testing throughout the software development lifecycle of the project, bringing down silos between the different phases and shortening release cycles from months to weeks in what is called sprints. As the name states, the model increases the agility through continuous planning, improvement, team collaboration, development and delivery, and responses to change. However, the operations teams are left out given that infrastructure and operations did not require the same agility at that time. The birth of cloud computing with its on-demand delivery of IT resources revolutionized software delivery. Before, software development and delivery required an iterative approach while the infrastructure remained rigid. With the adoption of the cloud, the need for owning and maintaining physical data centers was replaced by renting them out from cloud providers using different flexible payment models, for example, the pay-as-you-go model. Cloud computing came with several benefits, including but not limited to agility, by providing ease of access to a wide range of compute resources on demand, allowing for the creation of complex resources in minutes. Elasticity. Resource misutilization is no longer a problem, especially with the ability to quickly modify the compute resources based on the varying needs. And finally, cost saving. The pay-as-you-go model and the elasticity of the resources permit the users to continuously optimize the cost of the compute resources. With the adoption of cloud computing and software delivery, development and operations teams can no longer be siloed, as is the case with the Agile model. As a matter of fact, the development and management of the infrastructure must now align with that of the application itself. In light of the above, DevOps is a bouquet of philosophies, sets of tools and practices that aim to decrease the cost, time, and complexity of delivering software applications by unifying both the software development and infrastructure management processes. DevOps aims to automate as many processes as possible to reliably and efficiently create and manage infrastructure resources, release software changes, perform necessary tests, for example, unit, integration, stress tests, etc., automatically spin new environments seamlessly, enhance system security, ensure scalability, and improve collaboration. Having said this, in my opinion, DevSecOps, SysOps, MLOps, CloudOps, and all these variations can all be replaced by the term DevOps. Clearly, DevOps is nothing more than a set of philosophies and best practices to enhance the software delivery using today's existing technologies. Therefore, DevOps is not deployment of software on the cloud using the agile approach. Most of today's understanding confuses this with DevOps. It is also not creating software using the microservices approach. It is also not using infrastructure as code tools with no clear purpose. And finally, it is not the adoption of unneeded automation tools in general. Many entities attempting to apply DevOps might fall for the misconceptions listed above, and rather still apply unknowingly the agile model but on the cloud. The inability to truly define DevOps resulted in creating a lot of inefficient and weird job positions that might not necessarily contribute to the software development lifecycle. Worse, this can lead to the further deterioration of the quality of the application and the lifecycle as a whole. In light of the above, DevOps engineers are not engineers who create cloud infrastructure. Those are site reliability engineers. They are also not Kubernetes gurus. Those are just Kubernetes gurus, not DevOps engineers. And finally, they are not cloud enthusiasts. In brief, a DevOps engineer is someone with enough skill set to bridge the gap between the development and operation team through creating the required infrastructure, deploying the application, providing continuous delivery mechanisms, and automating all the processes previously done manually by the different departments, for example, the development, testing, security, etc. DevOps engineers must have a strong background in system administration and software development. In conclusion, DevOps is still a confusing term for most of the tech industry. Several definitions have been created without clear understanding and straightforward value. DevOps is nothing more than a culture that further enhances the software delivery life cycles. Becoming a successful DevOps engineer requires you to have a strong knowledge in both development and operations. Hi, and welcome to this lecture entitled Introduction to Web Application. Currently, thousands of applications are deployed and managed every day on dynamically created network resources. Technology advancement allowed for most of these operations to be carried out quickly and efficiently through processes and automation tools. Fullstack and DevOps engineers are two of the main pillars of realizing the software delivery. Computers in the 60s were the size of a room. As opposed to today, data exchange between computers was not a walk in the park. In fact, to access data stored on a computer, one had to either physically travel to the computer site or have the magnetic tapes holding data shipped through the traditional mailing system. Imagine the hassle of doing that. However, in order to appreciate the present, it is essential to go back to the beginning and understand what is everything and why. In this session, we will go back in history and understand what the Internet, the World Wide Web, and client-server architecture actually are, and understand the basics of name resolution and load balancing. 4 demos, as can be seen in the slides, will be performed to apply the knowledge learned in this lecture. Let us start with what is everything and why. The Internet is a global network. It's a network of networks that allows computers and other electronic devices to communicate and share information with each other. Initially used by very few academic and research institutes, its use and importance increased over time. The TCP/IP protocol standardized the connection of computer systems to the Internet, leading to the Internet being adopted by the public. The World Wide Web, also known as the web, constitutes an interconnected repository of documents accessible through the Internet using a browser. The Internet and the World Wide Web are not the same things. The former provides connectivity between computer systems across the globe. The latter is an application built on top of the Internet. The web as we know it today is composed of several components, the most important of which are the HTTP protocol, which standardizes data exchange between clients and web servers, uniform resource locators and uniform resource identifiers to access unique documents, and the hypertext markup language for building web documents. Finally, a web application is, as the name states, an application that is served through the Internet and consumed by a client through a web browser. Web applications are platform agnostic, meaning they can run on any machine using a browser. Examples of popular web applications include, but are not limited to, Google, Facebook, YouTube, and Gmail. Having learned the basics of the Internet, the World Wide Web, and web applications, this diagram depicts how everything is connected together to form what we enjoy today and collectively call the Internet. The Internet is the tool that allows all the other networks to be interconnected. As can be seen, public clouds such as AWS, email applications, web servers, private data centers, personal computers, and mobiles are all interconnected through the Internet. The client-server architecture is a computing model to serve and consume web resources. In this model, clients, for example mobiles, laptops, IoT devices, etc., consume resources from applications hosted on remote servers. In order for the client to fetch the web application, an HTTP request must be made to the server using its IP address. The web server listens and serves the application through a port. Evidently, it is impossible and impractical for the user to communicate with the servers using their IP addresses. In addition to the technical complexities that may arise, which are out of the scope of this session, imagine the experience of having to communicate daily with dozens of applications using their IP addresses. To solve this problem, domain resolution, which is mapping domain names to these IPs, were invented. With domain resolution, websites are accessed using domain names, which are translated by specialized servers to their desired IP addresses. The picture here shows the IP address of Google and Facebook. A domain name system is thus a database system containing all the registered domain names and their corresponding IP addresses. When a user types google.com in their browser, for example, the request performs the following trajectory. Note that the diagram is oversimplified. First, the request leaves the client all the way to a DNS server. The DNS server returns the IP address of google.com to the browser. Then another HTTP request is made to the IP address. Finally, the Google web server returns to the client the web page to be rendered. Modern day web applications can serve thousands or even millions of requests per second. Moreover, due to the advancement of the services online, requests may be resource intensive, for example, streaming, transferring large data, persistent connections, etc. To cater for such requests effectively, one server, no matter how large, is neither a guarantee nor a best practice. A better alternative would be to horizontally scale, that is to add multiple replicas of the server running the same application and distribute the load across them. A load balancer is a network appliance, be it hardware or software, that sits between the application servers and the clients, acting as an entry point to the system and distributing traffic based on customized rules. Load balancers come with great advantages. One of them is performance, through distributing the load across multiple servers. Availability, through distributing traffic across healthy replicas, in addition to solving the single point of failure issues. Scalability, through the ability of adding and removing servers upon need. And finally, security, through filtering traffic based on custom-defined rules. Load balancers can route traffic to the backend servers using different algorithms. First, we have round robin, which is a simple solution to distribute the traffic on all servers by rotation. This method does not take into account the server performance. Least connections distributes traffic to the server with the least number of connections. Least response time distributes traffic to the server with the fastest response times to health checks. And finally, least bandwidth distributes traffic to the server serving the least amount of bandwidth. Health checks is a mechanism offered by most load balancers to continuously monitor the health of the backend servers and distribute the traffic accordingly. With a proper setup, a load balancer may detect failed nodes and avoid distributing traffic to it until it is repaired. Some of the important parameters to configure when setting up health checks are the protocol to use, the port to perform the request on, the health check path, health check interval, which is the amount of time between health checks for a specific target, unhealthy threshold count, which is the number of consecutive failed attempts before considering a target as unhealthy, and finally, healthy threshold count, which is the number of consecutive successful attempts before considering the target as healthy. Hi, and welcome to this demo entitled Deploy and Serve a Static Website. In this demo, we are going to deploy a simple HTML website on an AWS EC2 Ubuntu machine. To do so, we are going to create a simple HTML page, create the networking and compute resources required on AWS, then we will install on the machine the Apache 2 web server, deploy the HTML page, and finally we will configure the web server to serve the application on port 80. So the first thing that we should do is actually create the SSH key pair so we can SSH to the machine. So let me start by doing that. I will click on create key pair, I will give it a name, and I will leave everything else as default. Now the key pair is deployed on my machine, but in order to be able to SSH, I have to move it to a hidden directory. Oh, let me get it from the downloads folder, and I will place it in the .keypairs hidden directory that I had already created. Now it is over here, and I will change the permissions to read only, and that's it. Now I also have to create a security group. Let us do that. So create security group. I will call it AWS demo. I will also call the description AWS demo, and I will add two inbound rules. One to allow me to SSH from anywhere, and one to allow requests on port 80 from anywhere as well. And I will create the security group. Finally, I will create an Ubuntu instance. I will give it a name called web server. I will use the Ubuntu 20.04 AMI, and I will use the t3.medium instance type, but you can use, of course, any type that you want. I will use the AWS demo key pair and the AWS demo security group, which allows inbound rules on port 22 and 80 from anywhere. I will add a little bit more of storage, and then I will launch the instance. So now the instance is being initialized, and it will take a little bit of time. So I will pause the video and I will continue after the instance is ready. Okay, as you can see now, the instance is ready. So I will SSH inside it using its public IP. Let me get the public IP. So SSH Ubuntu at public IP, and I will use the AWS demo key that I had created. Awesome. So now I am inside the machine. Now I want to actually install Apache. So to do so, I will update the package index to reflect the latest changes in the packages. This will take a few seconds. And now I will install Apache, which will also take a few seconds. Now, once installed, I can test the configuration that it is working by hitting the IP and port 80 of the machine. When done, Apache should return its default page. Let us try to do this. I will copy the public IP, paste it on the browser, and there you go. Apache returned its default page. So now we are sure that all the configuration that we have done so far is correct, since we can hit the machine on port 80. So now it is time to actually deploy the custom HTML page on the machine. Now to do so, there are a few steps to be done. First, I will create a directory in which I will deploy the application. So var www.myfirstapp is the name of my directory, and I will change the ownership from root to www.data, and then I will create inside this directory an index.html file, and I will paste the HTML document inside it. So there you go. It has a title called My First Application and a small paragraph that says I have no idea what I'm doing. Let me save it. Now that the application is deployed, I will also create a directory for the logs. This will be used by Apache to log the requests and the errors, and I will also change the ownership from root to www.data. Now the final step is to actually create a virtual host. The virtual host will instruct Apache on what to do when it receives requests. So let me do that. I will create a file called myfirstapp.conf inside the etc apache 2 sites available directory, and I will paste this virtual host that tells Apache that please listen on port 80, and whenever you receive a request on port 80, you have to load to the client the document whose root is found in this directory. In addition to that, please log all the error logs in this directory and all the requests in this directory. So I will save, and now I have to enable this configuration file using the ansite command, and I will disable the default configuration. I will also check that all the syntax of my configuration is correct. It says syntax OK. And finally, I will restart Apache. Now, if I hit the machine using its public IP and on port 80, the default page will no longer be returned. Instead, it will return the custom HTML page that I had already deployed. So let us try to do this. And there you go, success. Hi, and welcome to this demo entitled Deploy and Serve Two Static Websites. In the previous demo, we installed Apache and we configured it to listen and serve a static website on port 80. In this demo, on the same machine, we are going to create a second HTML page and we will deploy it, and then we will configure the web server to serve the application on port 81. First, let us make sure that the first application is still running. It is still running. Now, I will SSH again to the machine. I am inside the machine. And then I will start by creating the directory in which I will deploy the code. Then I will change the ownership from root to www.data. Then I will create the index.html file. And I will paste the second application code, which is almost similar to the first one. I will save it. Then I will create the log directory, and I will change its ownership as well. Finally, I will create another virtual host to tell Apache what to do when it receives requests on port 81. This virtual host instructs Apache that it is listening on port 81, and whenever it receives a request on port 81, it will load the documents that are present in the var www.mysecond_app, and I told Apache where to place the error and request logs. So finally, I will save. I will enable the configuration. I will test the syntax. And finally, I will restart Apache. Now, I will try to hit the machine using its public IP on port 81. Unfortunately, it's not working, but this is normal because the security group attached to this machine does not allow requests on port 81. So let us change this. Let's go back to the security group and modify the inbound rules and add another rule, custom TCP port 81 from anywhere. Save. Now let's test again. So I will get the public IP, paste it, port 81, and it still won't work. But this is also normal because by default Apache does not listen to port 81, and we have to enable it for it to work. So let us do that. We will edit the ports.conf file inside etc apache 2, and we will add this line that says please listen on port 81. I will save, restart Apache, and now I will test again. There you go, it's working. So now I have an application running on port 80 and another one running on port 81 on the same servers. Hi, welcome to this demo entitled Add Domain Names to the Application. In the previous demos, we deployed two HTML applications on one EC2 machine. One application is served on port 80, while the other one is served on port 81. Instead of serving the applications using the IP address of the machine and on different ports, we will use in this demo domain names, and both applications will be served on port 80. So the first application will be served using domain name myfirstapp.com, and the second application will be served using domain name mysecond.app.com. So let's do this. I am logged into my machine. So first of all, I will modify the virtual host of the first application. Since it is listening on port 80, we will not modify this one, but I will add the server name directive, which is myfirstapp.com. So now this virtual host will listen on port 80 and will serve requests coming with the server name myfirstapp.com. Let me save this. And now I will modify the virtual host of my second app. So let's do this. Now, as you can see, it is listening on port 81. I will change this to listen on port 80. And I will add the server name directive that is listening using server name mysecond.app.com. And now I will restart Apache. Now the last thing to do, since we are using fake domain names, I need to instruct my machine on how to translate the domain names into the corresponding IP address. So to do so, I have to modify the host file on my machine. Let me do this. I will open a new tab and modify the host file. So I need to add the IP address of the machine and the domain names. So this line instructs my machine that whenever I put in my browser either myfirstapp.com or mysecond.app.com, translate it to this IP address. So let's try it now. Let me go into the browser, get the, so I will add firstapp.com. And as you can see, the first application is loaded. Now let me try it for mysecond.app.com. And there you go. I have my first app loaded using myfirstapp.com, and I have my second app loaded using mysecond.app.com. Hi, and welcome to this lecture entitled Web Application Concepts. So far, we have learned to deploy and serve websites using Apache web servers. Moreover, we leverage the power of load balancing in order to scale the website when needed. Unfortunately, life is not this straightforward. As a matter of fact, with great innovation comes great complexity. With the internet and technological advancement, websites are the simplest forms of applications created and deployed. Web applications, on the other hand, are more complicated to design, develop, deploy, and maintain. This lecture provides a deep dive into web applications with the aim to understand their nature, importance, characteristics, and challenges. In this video, I will discuss the differences between websites and web applications, the HTTP protocol, and the web application layers, components, and architecture. Websites versus web applications. By definition, websites are a set of interconnected documents, images, videos, or any other piece of information developed using HTML, CSS, and JavaScript, and deployed and served using one of the ways we introduced previously. User interaction with websites is limited to the user fetching the website's information only. Moreover, websites are usually stateless, and thus requests from different users yield to the same results at all times. Examples of websites include but are not limited to company websites, blogs, news websites, etc. Web applications, on the other hand, are much more complex than websites and offer more functionalities to the user. Google, Facebook, online gaming, e-commerce platforms are all examples of web applications. Such applications allow the user to interact with them in different ways, such as creating accounts, playing games, buying and selling products, etc. Evidently, in order to provide such complex functionalities, the architecture of the web application can prove to be much more complex than that of a website. As already discussed, in its simplest form, most web applications follow the client-server architecture, in which a client application is loaded from the server to the browser, allowing communication with the web application on the server through the internet using the HTTP protocol. Communication between application components happens through the Application Programming Interface, or API. Now let us discuss the HTTP protocol. By definition, the Hypertext Transfer Protocol, or HTTP, is a protocol designed to load web pages deployed and exposed on the internet. The protocol is designed to standardize the exchange of information between connected devices. To better understand the protocol, consider this diagram. A typical flow begins when the client machine sends an HTTP request to the server. The server takes the appropriate action and responds with an HTTP response, which will be processed by the client. Communication over HTTP is done using HTTP messages. It can either be an HTTP request from the client to the server or an HTTP response from the server to the client. Usually, HTTP requests and responses are composed of the same structure and components with some minor differences. The first component to discuss is the HTTP method, which is used to indicate the desired action. Some of the methods include GET, which is used to fetch data from the server, POST, used to create new data on the server, PUT, used to modify existing data on the server, and DELETE, used to delete data from the server. The HTTP version is used to indicate the version of the HTTP protocol used. HTTP Uniform Resource Locator, or URL, constitutes the complete address of a resource on the web. It is unique per resource. A URL can be composed of multiple fields. Dissecting the URL in this picture results in the following. The protocol is HTTP. The domain name is mywebapp.com. The application port is 80. The path is /some/API. And the rest are the query string parameters. HTTP headers include information about the request or response, stored in key value pairs. The HTTP headers provide more context and information to the HTTP request. For example, headers specify the accepted languages, preferred media format, etc. The HTTP body contains the information sent by the client to the server or vice versa. Finally, the HTTP status code dictates the status of the requests. Some of the most widely used status code blocks are 2XX to indicate a successful completion of the request, 4XX to indicate a logical error while serving the request, for example 404 not found, 5XX to indicate a server error while serving the request, for example 504 unable to reach database. An application is divided into 3 layers. More layers can be added to the application design, but for simplicity purposes, this lecture explains only 3. The first one is the presentation layer, also known as the client side. The client applications are designed for the user to interact and manipulate the application. Front-end applications are developed using many technologies, for example, AngularJS, React.js, Vue.js, etc. Application or business logic layer is part of the application server side. It accepts and processes the user requests and interacts with the database for data modification. Such applications can be developed using Node.js, Python, PHP, Java, etc. And finally, we have the database layer. This is where all the data resides and is persisted. Usually, a website is composed of a simple code developed entirely using HTML, CSS, and JavaScript alone. On the other hand, web applications are more complex and are made of different components. In its simplest form, a web application is composed of a front-end application, which represents the client side, and is used to allow the user to interact with the application. The backend application, which represents the server side and is used to serve the user requests. A database to store and load the application and user data. The components above are essential to create web applications. However, the latter may require additional components to serve more complex functionalities in a more optimized way. For example, an in-memory database for caching, a message bus for asynchronous communication, content delivery network for serving and caching static content, a workflow management platform for organizing processes, and many other components. Clearly, as the application's use case grows in size and complexity, so will the complexity to design it. Therefore, a proper way to architect and organize the application is needed. Here is a diagram representing the architecture of an e-commerce web application that I designed and deployed on AWS a few years ago. You can clearly notice the amount of interconnected components required to make it work. Web application architecture mainly depicts the way the different components are built and interact with each other. As a matter of fact, as the application grows in size, a well-tailored architecture is essential to ensure the proper functioning of the application. There exist multiple architectures when designing web applications. Nonetheless, two of the most prominent ones are monolithic and microservices. To better understand the difference between microservices and monolithic applications, consider the example of building an e-commerce platform. Typically, such a platform contains several functionalities, namely catalog to serve and display available items, customer to handle customer-related functionalities, order to manage orders happening on the platform, and payment to allow online payment functionalities. From a monolith perspective, all the aforementioned functionalities are designed using one technology, for example Java, PHP, or Node.js, having one large code base and deployed entirely on one server. Each functionality is designed as a separate module which interacts with one another through requiring each other. On the other hand, if designed using the microservices approach, each functionality turns into a separate and independent service, most probably with its own database too, that is developed, deployed, and managed on its own. Evidently, both approaches possess numerous advantages as well as disadvantages. Monolithic applications indeed provide several attractive advantages, especially the ease of management, since they are very easy to develop, deploy, and test. Unfortunately, the aforementioned advantages begin disappearing as the application grows in size. As a matter of fact, monolithic applications comes with many great disadvantages, especially at scale. One of them is slower development life cycle. As the size of the application grows, so does the amount of time and complexity required to build, test, and deploy the application at every change. And with scale, changes are more frequent. Evidently, the bigger the application, the slower it will become to continuously develop and publish the application. Code dependency. No matter how organized one can be, organizing the aggregation of the code in one place and the communication between modules becomes inefficient and inconsistent at the end. Performance issues. As the functionalities grow in size and complexity, maintaining a proper performance becomes an issue. In fact, the different services and capabilities of the application will require further capabilities and resources from the hosting server. Moreover, having different functionalities may require different specialized infrastructure for different types of functionalities, which may prove to be difficult to achieve given the centralized nature of monolith, since everything is deployed on one server. Scalability issues. Scaling a monolith becomes inefficient at scale. Typically, different parts of the application may require different scalability rules. For example, considering the e-commerce application, assume most of the traffic is directed towards the catalog module, whereas all the remaining ones are receiving minimal traffic. In the case of monolith, all of the application will have to be scaled out using large servers, although only one small part of the application requires it. Infrastructure cost. Provisioning resources to operate the monolith may prove to generate unwanted costs. Code ownership and team division problems. Due to the interconnected nature of the code in a monolith, onboarding members on the team and clearly dividing responsibilities between them becomes problematic. Technology lock-in. Being centralized in one code repository, all of the application with its different functionalities is developed using a specific set of technologies. However, this may prove to be costly, as each technology has advantages and disadvantages. Being locked to one stack not only forbids the application from the advantages of the available technologies, but it may affect its performance as well. Technical debt. Technology is advancing rapidly, and platform changes with enhancements are being rolled out quickly. As the monolith grows, upgrading it becomes costly, which may affect the performance and the continuity of the application. And finally, single point of failure. A failure in one method, service, or endpoint may lead to the failure in the whole application. Clearly, centralized architectures, especially monolithic applications, come with great advantages, especially for simple applications on small scales. It is intuitive to design, develop, deploy, and maintain them. Unfortunately, the above disappears quickly as the application and the maintaining team grows. Microservices, on the other hand, alleviate most of the monolith disadvantages due to their extremely distributed nature. The first advantage is fault tolerance. Due to their distributed and independent nature, failure in one microservice should not bring all of the application down. Therefore, single points of failure and downtimes are minimized. High scalability. Microservices allow to have different scaling mechanisms and rules for different microservices depending on the nature of the traffic and resource consumption of each of them. This allows for a more optimized resource utilization and scalability rules. Ease of maintenance. Even if the application grows in size and complexity, teams can be organized to work independently on different microservices. With proper communication between teams, the main things to agree upon are the exposed endpoints and communication between services. For instance, the catalog service and the order service can be developed and maintained separately by completely different teams. The teams must only collaborate on exposing and using the endpoints of each service, assuming that one service will have to communicate with the other. Ease of deployment. It is easier and faster to build and package a small microservice, especially with today's powerful automation tools, and serve them on smaller commodity servers. Technological freedom. Each microservice can be designed, developed, and maintained on its own using the most convenient set of tools and technologies, and regardless of the other microservices forming the application. This provides a great advantage by allowing teams to leverage the existing choices in technologies and use those that fit the purpose of each functionality. For example, the catalog service may be developed using Node.js, while the customer service is developed using Golang. Fast development life cycles. Developers working on specific independent and small-scale services allows the services and the overall application to be maintained and updated with fast development and release cycles. Despite their many advantages, microservices come with multiple disadvantages, which must be considered and addressed by teams willing to develop software using this architecture. The first one is complex infrastructure. The distributed nature of microservices dictates a more complex infrastructure to be created. As a matter of fact, as the number of services grows, each of which requiring its own setup, rules, configurations, and scalability rules, a proper infrastructure capable of serving these different needs is required. The need for DevOps. Microservices are decoupled from each other. However, microservices and their underlying infrastructures are highly coupled. Deploying and managing microservices is quite different than that of a monolithic application. Developers and operations teams must collaborate efficiently to ensure that the application and infrastructure being developed work well together. This entails both teams to understand each other, learn additional skills, and continuously coordinate. Increased network calls. Microservices are deployed on different servers, different subnets, and in different physical locations. Moreover, a simple request incoming to a microservice application genuinely must traverse multiple services and components, each reached through a network call. This greatly enhances the need for a robust infrastructure. And finally, complex end-to-end testing. While unit testing may be a great advantage with microservices, end-to-end or integration testing may not be as pleasant. As a matter of fact, as the number of services and components grows, automation tools and robust testing processes are required to continuously create test beds and successful test scenarios at every release, which may prove to be complex and costly at the same time. Hi, and welcome to this demo entitled Enable Load Balancing. To better understand load balancing, we are going to create 3 Ubuntu EC2 machines on AWS. And we will create 2 simple HTML pages. We will deploy the first one on one VM, we will deploy the second one on the second VM. And the third VM will be configured as a load balancer using Apache, and we will instruct it to distribute the load on the first 2 virtual machines. Now, to save time, I already did some of the work. So on the first server, which is app1, I installed Apache and I deployed the first application. I did the same thing on app2 and I installed Apache on the third virtual machine. So first of all, let us test that the configuration that I have done is working correctly. I will hit the first server and the first application is returned. I will now hit the IP of the second machine and the second application is returned. Now I will hit the load balancer machine, which has only Apache installed, and it will return the default Apache page. So far everything I have done is working correctly. Now what I will do in this demo is that I will configure Apache on the load balancer machine to actually work as a load balancer. So the first step is that I have to enable a few modules for Apache to work as a load balancer. So I will do this on the third machine. There you go. And now I will configure a virtual host, which is going to be a little bit different than the one we used to do before. So let me paste it and I will explain what it means. So I'm instructing Apache on this third VM is that you will listen on port 80, and whenever you receive a request, you are going to route it either to the first member, which is the first virtual machine, or the second virtual machine. Now all I have to change is to put the IPs of each machine instead of these placeholders. Now let's do that. So I will get the IP of the first machine and I will replace it here. And I will do the same for the IP of the second VM. And I will save the configuration. Now I will disable the default virtual host and I will enable the load balancer virtual host. I will test my syntax, and finally I will restart Apache. So now if I hit the load balancer machine, it's supposed to route me one time to the first virtual machine and load the first application, and the other time to the second virtual machine and load the second application. Let's test it. So I will get the IP of the load balancer and I will place it in the browser. So now it loaded the first application. Now if I hit it again, it loaded the second application. Now if I repeat the steps, it will keep on distributing the load across the 2 virtual machines. And this is load balancing. Hi, and welcome to this lecture entitled Introduction to Server-Side Applications. After learning different concepts about web applications, such as the differences between websites and web applications, and web application layers, components, and architecture, we are going to focus in this video on the application server side. In this video, we are going to discuss different database concepts, and then we will discuss the NK backend service, which we will deploy on AWS in the next video. A database is a software program that enables capabilities to efficiently store and query data in a system. Almost every system in the world includes some sort of database that manages the data. For example, smart devices, mobile phones, etc. Most of today's web applications rely on constantly changing data. For instance, Facebook and Twitter are all examples of web applications with a massive amount of data flowing in and out of the system. Therefore, there must be a reliable way to store and manage all this data. A database management system, or DBMS, is a software program that enables the creation and management of databases and data models, thus providing efficient tools for managing the data. MySQL, MongoDB, and ArangoDB are all examples of DBMS. Database management systems are designed with multiple tools and capabilities, such as a database engine, data query language, monitoring tools, and user management tools. An application's data may grow to become extremely complex. Moreover, the application needs to constantly store, generate, modify, and remove data from the database in a dynamic and reliable way. Data models are design processes to organize the way the data is managed. Consider the e-commerce application explained in the previous lecture. Such an application must manage data related to the catalog, for example, product description, product prices. Data related to the customer, for example, name, age, address. Data related to orders generated on the system, such as order details, products purchased, and data related to payments, such as credit card information and transaction records. Clearly, each service requires different types of data to be stored. A data model allows the developers to logically structure this data in different tables and collections in a way to reliably store and fetch the required data. Different database types currently exist, each supporting a distinct data model. Of all existing database types, this lecture explains relational databases, document databases, and graph databases. Relational databases are based on the relational data model, which organizes data into tables. Each column in a table defines an attribute with characteristics. Each row in a table corresponds to one record and is identified by a unique ID. For instance, to store the names and ages of all students in a university, a relational database can be used. As an example, a table called students can be created with two attributes, name of type string and age of type integer. Moreover, several tables can be created referencing one another. For instance, another table called courses containing a list of all available courses in the university has two properties, name of type string and is available of type boolean. Finally, a third table called student to course registrations can be created to keep track about student registration to the courses with two columns, one corresponding to the student ID while the other corresponding to the course ID. Structured query language, SQL, is one language used to query the data from the structured databases. As a matter of fact, SQL provides efficient capabilities to manage data in much more complex and large data models. Examples of RDBMS and relational databases include MySQL, Oracle Database, and PostgreSQL. Relational databases are best used when the data in the system is highly structured and doesn't change frequently over time. A document database is a type of non-relational database designed to manage, which is store and query data in JSON formatted records. Such databases provide more flexibility, especially for the developers, due to their loose model that can change dynamically over time and between records without much administrative overhead. Modeling the university example presented earlier results in three JSON documents as can be seen in the picture. Query languages are provided by the vendor to manage the data. Document databases are best used for use cases similar to catalogs, user profiles, and new projects that need to be built with agility in mind. Examples of document databases include MongoDB, Amazon DocumentDB, and Cosmos DB. Graph databases are NoSQL databases that store data without schemas, while connecting the records in each table using relationships. Data records are stored in what is known as nodes. Nodes can have relationships with one another using edges. Graph databases combine the flexibility of NoSQL databases with the power of relational databases. The university example is depicted in this diagram. The student node stores JSON records, each of which represents information about a student. The courses node stores JSON records, each of which represents information about a course. The student to course registration is of type Edge and stores JSON records related to the registration of each student to each course. Edges must have valid database record IDs, one for the student and another one for the course. Graph databases offer a flexible data model, as well as a robust way to manage relationships between data points. Therefore, although graph databases can be useful in most use cases, they are most widely used in fraud management systems, identity and access management, and recommendation engines. Examples of graph databases include ArangoDB and Neo4j. This diagram summarizes how a web application is deployed on AWS and how users interact with it. Consider an application consisting of a front-end application, back-end application, and a relational database. One way to deploy it is as follows. The database is deployed and served using AWS Managed Database Service or AWS RDS. For security purposes, it is recommended not to expose the database directly to the internet, meaning deploy it in private subnets and properly secure the access. The backend application is deployed on an EC2 server with a public IP. The front-end application is deployed and served on AWS S3. All the application components reside within an AWS virtual private cluster. A typical HTTP request response cycle is as follows. The client sends an HTTP request to the front-end application. The front-end application code is returned and is loaded on the client's browser. The client sends an API call through the front-end application to the back-end application. The back-end application validates and processes the request. The back-end application communicates with the database for managing the data related to the request. And finally, the back-end application sends an HTTP response containing the information requested by the client. The NK backend service is an open source project that serves as a basic backend service. The service is developed using Node.js and Sails.js. The service uses ArangoDB to store and manage its data. It is a RESTful service and exposes CRUD APIs to manage person records. It contains the following APIs. Get health, which is the health endpoint. It is used to ensure that the service is up and running. Post person. It creates a person record in the database. The function performs a transaction against the database, checks if the person already exists using the email. If the person already exists, a logical error is returned. Else, the person record is created in the database and a success response is returned to the client. Get persons. It fetches all the existing persons in the database. And finally, delete person by ID. Deletes a person record from the database using the ID. In the next video, we will deploy the NK backend service on AWS. Hi, and welcome to this demo entitled NK backend service deployment. To better understand how an application is deployed and serves traffic over the internet, in this tutorial, we will deploy the NK backend service and its database on an AWS EC2 machine and explore some of its APIs by communicating with them using the Postman API client. The following steps will be completed. First, we will create an AWS virtual machine. Then we will configure it with the necessary prerequisites. Afterwards, we will deploy the database and connect to it using a client. And finally, we will deploy the backend application and perform some API requests to validate the deployment. The backend service and the database will both be deployed on one virtual machine. Moreover, the backend service will be exposed on port 8080 while the database uses port 8529 for communication. Therefore, to successfully perform the deployment, we will create a security group with the following inbound rules. Port 8080 to communicate with the backend application, port 8529 to communicate with the database, and port 2022 to SSH to the machine. Now to save time, I have already created the security group and the machine. As you can see here, there is a security group with the desired inbound rules and the Ubuntu 20.04 machine. So now I will SSH to the machine using its public IP at public IP and the AWS demo key. So now I am inside the machine. The first thing to install is the Arango database. Now the official ArangoDB documentation explains all the steps required to deploy the database. So I will start by updating the package repository. And then a bunch of other commands before updating the package repository again. And finally, installing the Arango database, which should take a few seconds. During the installation, the installer will prompt us to enter and confirm the root user's password. So I will put the password. And I will leave those questions as they are. And once the installation is complete, I will make sure that the service is running by checking its status. So the ArangoDB is now installed and is running. Now the first thing I will attempt to do is to actually connect to it using its client, and I will successfully not be able to communicate with the database. But this is normal because by default ArangoDB does not allow connections from outside of the VM. To solve this issue, the ArangoDB configuration file must be edited. So let us do this. I will edit the ArangoDB configuration file, and I will edit the endpoint to allow external connections. I will save the file, restart the ArangoDB service, and now I will attempt to connect to it again. This time it should work. Yep, it did. So now I will add the root username and password, and I will select the system database, which will redirect me to the administration console. The console provides me with different functionalities, such as the ability to create databases, perform queries, monitor performance and logs, etc. So reaching this point signals the success of the deployment of the database. Now it's time to actually deploy the backend service. As explained previously, the backend service is a Node.js RESTful service built using Sales.js. Moreover, the application code is stored on a public GitHub repository which everyone has access to. So in order to fully deploy and run the backend service, some prerequisites must be installed. First of all, I will update the package repository again. And then I need to install Git. In brief, Git is an open source tool for source code management. Git allows teams of developers to collaborate together and track changes efficiently happening on the code while storing the code safely in a remote repository. In this demo, we will use Git to download the backend service from the GitHub repository to the server. So first of all, I will install Git. And I will make sure that it is installed using the git version command. And this shows that Git is already installed. So now the next step is to actually install the Node.js platform. So to do so, I will install Node.js and npm using the apt-get tool. So now that Node.js is installed along with npm, I will clone the repository on the server, and I will go inside the directory. So the application code is successfully installed on the machine. For simplicity purposes, understanding the use of the different files is out of scope. Rather, in this demo, we focus on the system requirements for the application to run. Being a Node.js application, the service requires some packages to be installed. Therefore, to do so, we will install the packages using the npm install command. Finally, the application depends on some environment variables. Environment variables are very similar to global variables in any programming language. Once a global variable is defined in a file, it can be accessed from anywhere inside that file. Similarly, environment variables are system-wide variables in Linux. Once an environment variable is exported, it can be used by any process on the machine. So let us start by exporting the environment variables of the application. The first one is the port. It tells the application to use port 8080. Next, we have 5 environment variables related to the database credentials, such as the host, port, username, password, and finally the database name, which is persons. And finally, the application requires 5 more environment variables that we don't really have to care about, but they are necessary for the application to run. Finally, I will run the application using the node app.js command. The application logs clearly show that the application successfully connected to the database and created a database called persons as well as a collection with the same name. So to validate the creation of the database, I will log back into the database administration console. So let's do this. I will go back here, and as you can see, there is a persons database which I will select, and there is a persons collection which is empty. This was created by the application. So now I will validate that the deployment is successful and that the application is reachable from my machine using the custom health API. So I will use the Postman client, which I have downloaded over here. I will put the machine IP, port 8080, and the forward health. And there you go. We have a successful response indicating that the backend service is running. So now, to test the available APIs, we need to download the Postman collection, which you can find in the repository, and import it to the Postman API client. Now I have already done so, and as you can see, there are 3 APIs. I will only test one API, which is create person. Now before I do so, I have to change the variables to reflect the server's IP address. So let's do this now. I will put the correct IP address and the correct port. And finally, I will hit the create person API, which has a JSON body over here. So this information should be added to the database if everything is successful. So let's send an API. And there you go. I have a successful response indicating that this database record has been added to the database. Now we can validate it through the application logs, which clearly indicate that the application received the request, it added to the database, and it returned a response to the client. And finally, I will go back to the database and refresh the persons collection, and I can see the record that is added over here. Hi, and welcome to this lecture entitled Infrastructure Types. Currently, there exist multiple infrastructure types to deploy and manage web applications. Each option possesses its own advantages, disadvantages, and use cases. Moreover, a combination of more than one type can be used together to create the desired infrastructure. In this lecture, we discuss 4 of the most popular infrastructure types: physical servers, virtual machines, containers, and serverless. This diagram lists different infrastructure options for deploying and managing applications. To better understand the difference between each type, consider a scenario where company X requires 2 applications, A and B, to be deployed. Let us begin by talking about physical servers. In this type of infrastructure, the company would have to purchase, configure, and manage a physical server in a physical location, for example, a data center. Moreover, once configured and an operating system is installed, both applications A and B can be deployed on the server. The company must ensure the correct configuration and management of the server and application throughout its life cycle. Physical servers have many advantages, being customizable and giving powerful performance through full dedication of the server resources to the application. However, some of the disadvantages include large CapEx and OpEx, since setting up the required infrastructure components may require a large upfront investment, in addition to another one for maintaining the resources. Management overhead. to continuously support and manage the resources. Lack of scalability. In fact, modifying the compute resources is not intuitive and requires complicated labor work and a lot of time. Risk of over or under provisioning due to the lack of scalability. Performance degradation, since hardware components will degrade and fail over time. And finally, improper isolation between applications. All the applications deployed on the same physical host share all the host resources together. Virtual machines. One of the best practices when deploying web applications is to isolate the application components on dedicated environment and resources. Consider an application composed of several components: a MySQL database, a Node.js backend API service, a .NET backend consumer service, a React.js frontend, and RabbitMQ. Typically, each of these components must be properly installed and configured on the server with enough resources available. Deploying and managing such an application on physical servers may become cumbersome, especially at scale. In fact, deploying all the components on one physical server may pose several risks. For example, improper isolation for each application component, race conditions, deadlocks, and resource overconsumptions by components. The server also represents a single point of failure. Deploying the components on multiple servers, on the other hand, is also not an intuitive approach, especially due to cost, lack of scalability, and all the other disadvantages that we already discussed. Virtual machines represent the digitized version of the physical servers. As a matter of fact, hypervisors, for example, Oracle VirtualBox, Hyper-V, and VMware, are software solutions that allow the creation and management of one or more virtual machines on physical server. Different virtual machines with different flavors can be created and configured on the same physical host. For example, one physical server may host 3 different VMs, each with its own dedicated resources and operating system, and can be managed separately from the other ones. Some of the advantages include low capital expenditure, since there is no need to buy and manage hardware components. Flexibility, through the ability to quickly create, destroy, and manage different VM sizes with different flavors. Disaster recovery. Most virtual machine vendors are shipped with solid backup and recovery mechanisms for the virtual machines. Reduced risk of resource misuse. And finally, proper environment isolation. Some of the disadvantages include performance issues. Virtual machines have an extra level of virtualization before accessing the compute resources, rendering them less performant than the physical machines. Security issues. Multiple virtual machines share the compute resources of the underlying host. Without proper security mechanisms, this may pose a huge security risk for the data in each virtual machine. And finally, increased overhead and resource consumption. Virtualization includes the operating system. As the number of virtual machines placed on a host increases, more resources are wasted as overhead to manage each virtual machine requirement. While virtual machines digitize the underlying hardware, containerization is another form of virtualization, but for the operating system only. Container engines, for example Docker, are software applications that allow the creation of lightweight environments containing only the application and the required binaries for it to run on the underlying operating system. All the containers on a single machine share the system resources and the operating system, making containers a much more lightweight solution than virtual machines in general. A container engine deployed on the server, whether it is a physical or virtual machine, takes care of the creation and management of containers on the server. Some of the advantages of containers include decreased overhead. Containers require fewer resources than virtual machines, especially since virtualization does not include the operating system. Portability. Container images are highly portable and can be easily deployed on different platforms. A Docker image can be deployed on any container engine that supports it, for example Docker, Kubernetes, AWS ECS, AWS EKS, Microsoft AKS, Google Kubernetes Engine, etc. And finally, faster build and release cycles. Containers, due to their nature, enhance the software development lifecycle from development to continuous delivery of software changes. Some of the disadvantages include data persistence. Containers, although support data persistence through different mechanisms, are still considered as a bad solution for applications that require persistent data, for example, stateful applications, databases, etc. Up until today, it is not advised to deploy such applications as containers. Resource overhead and performance issues. Containers are more lightweight, require fewer resources for the underlying host, and generally perform better than VMs. However, being a virtualization technology, resource overhead and performance issues still exist with containers, especially when improperly configured and managed. And finally, cross-platform incompatibility. Containers designed to work on one platform will not work on other platforms. For instance, Linux containers do not work on Windows operating systems and vice versa. Serverless solutions, for example, AWS Lambda functions, Microsoft Azure functions, Google functions, mainly designed by cloud providers not long ago, are also becoming greatly popular nowadays. Despite the name, serverless architectures are not really without servers. Rather, solution providers went deeper into the virtualization, removing the need to focus on anything but writing the application code. The code is then packaged and deployed into specialized functions that take care of managing and running it. Serverless solutions paved the way for new concepts, especially function as a service, which promotes the creation and deployment of a single function per serverless application. For example, one function to send verification emails as soon as a new user is created. The diagram clearly showcases the architecture of serverless solutions. Application code is packaged and uploaded to a function, which represents a virtualized environment that is completely taken care of by the provider. Serverless architectures, although alleviate a lot of challenges presented by the previous three infrastructure types, is still unable to replace any of them due to its many limitations. As a matter of fact, serverless architectures do not meet the requirements of all use cases and therefore work best in conjunction with other infrastructure types. Most serverless solutions are offered by providers rather than being a solution that can be deployed and managed by anyone. Some of the advantages of serverless include cost. Users only pay for the resources consumed during the time of execution. Idle functions generally do not use any resources, and therefore the cost of operation is greatly reduced. Scalability. Serverless models are highly scalable by design and do not require the intervention of the user. And finally, faster build and release cycles. Developers only need to focus on writing code and uploading it to a readily available infrastructure. Some of the disadvantages include security. The application code and data are handled by third-party providers. Therefore, security measures are all outsourced to the managing provider. The security concerns are some of the biggest for users of the serverless model, especially when it comes to sensitive applications that have strict security requirements. Privacy. The application code and data are executed on shared environments with other application codes, which poses huge privacy and security concerns. Vendor lock-in. Serverless solutions are generally offered by third-party providers, for example, AWS, Microsoft, Google, etc. Each of these solutions are tailored to the provider's interests. For instance, a function deployed on AWS Lambda function may not necessarily work on Azure functions without code modifications. Excessive use and dependence on a provider may lead to serious issues of vendor lock-ins, especially as the application grows. Complex troubleshooting. In contrast with the ease of use and deployment of the code, troubleshooting and debugging the applications is not always straightforward. In fact, serverless models do not provide access whatsoever to the underlying infrastructure and provide their own generic troubleshooting tools, which may not always be enough. In conclusion, technology is advancing at a rapid pace. The reliance of software solutions is increasing by the day, and therefore, robust infrastructure solutions are required to efficiently deploy, run, and manage these software solutions. This lecture describes several infrastructure options, along with the advantages and disadvantages of each of them. Evidently, there is no best solution or a solution that fits all use cases. Rather, each infrastructure type favors a certain function or use case. To get the best performance, users must carefully assess each option or combination of options depending on their requirements. Hi, and welcome to this lecture entitled Introduction to Containers and Docker. With the rapid evolution of the software industry in general, developing and deploying web applications is not as straightforward as writing the code and deploying it on remote servers. As a matter of fact, today's software development lifecycle requires the collaboration of different teams, for example, developers, designers, managers, etc., working on different tools and technologies to serve the challenging application requirements and meet the customer needs in an organized and optimized way. Such collaboration may prove to be extremely complex and costly if not properly managed. Docker is a containerization software that aids in simplifying the workflow by enabling a portable and consistent application that can be deployed rapidly anywhere, thus allowing software development teams to operate the application in a more optimized way. This lecture explains different container tools and terminologies, namely container images, containers, container registries, Docker files, and container data management. Moreover, Docker is introduced and used to reinforce the information learned with examples and scenarios. A container image is nothing but a snapshot of the desired environment. A container uses an image as a starting point for that process. For example, a sample image may contain a MySQL database, or Nginx, or a customized Node.js RESTful service. An image is therefore a snapshot of an isolated environment, usually created by a maintainer and can be stored in a container registry. A container is then the running version of an image. A container registry is a service to store and maintain images. Container registries can either be public, allowing any user to download the images, or private, requiring user authentication to manage the images. Examples of container registries include Docker Hub, Amazon Elastic Container Registry, and Microsoft Azure Container Registry. As already mentioned, Docker is a container engine that aids in creating and managing Docker images and containers. A Docker file is a text document interpreted by Docker and contains all the commands required to build a certain Docker image. A Docker file allows the creation of the resulting image using one build command only. By default, Docker containers do not support data persistence. When a container no longer exists, all the data saved inside it will disappear. Worse, sharing data between containers cannot be achieved intuitively. One of the many ways to persist data would be to actually store them on the host machine rather than in the container itself. Therefore, even if the container crashes or is restarted or stopped, the data remains intact on the host machine. Docker presents two options for data persistence on the host machine: volumes and bind mounts. Docker volumes are created and managed by Docker. Volumes can either be created specifically by the client using the Docker volume create command, or automatically by Docker when mounted to a container. Volumes are usually stored locally on the host machine, for example inside the var lib docker volumes directory on Linux, and can also support volume drivers, allowing to store data on remote hosts or on cloud providers. A volume can be mounted into multiple containers simultaneously, either with read-only or read-write policies. Furthermore, volumes can either be named or anonymous. Docker ensures the uniqueness of the names of the volumes. Bind mounts serve the same purpose as volumes, that is, persisting data. However, bind mounts have limited functionalities compared to volumes and are not managed by Docker. Bind mounts can be located inside any file system directory, for example, /opt /some directory, or any other directory of your choice. In general, it is advised to always rely on named volumes rather than on bind mounts. Hi, and welcome to this demo entitled Introduction to Containers. To better understand the differences between the concepts explained in the previous lectures, in this demo, we will attempt to deploy a simple HTML application on an Ubuntu EC2 machine. Then we will containerize the application and redeploy it. The following steps will be performed. First, we will create the networking and compute resources on AWS. Then we will deploy a simple HTML application on an AWS EC2 machine. Afterwards, we will containerize the application and store the image on AWS Elastic Container Registry or ECR. And finally, we will deploy the containerized version of the application. Now I have already created the security group and the EC2 machine. I also installed Apache and deployed the HTML application. We have done all these steps many times before. So to test my setup, I will perform an API request using the machine's IP, and the custom page should be returned. So let's do this. I will put the machine's IP in the browser, and the custom page is now loaded. In conclusion, to deploy the application on the EC2 machine, several tools had to be deployed and configured. While this is manageable for one simple application, things won't be as easy and straightforward when the application grows in size. For instance, assume an application of 5 components must be deployed. Managing each component on the server will not be so easy. So in the next parts of this demo, we will show how containerization can remove such problems. So first of all, I will stop the Apache web server, and I will validate it by hitting the machine's IP again, and the custom page shouldn't be loaded anymore. Now it is time to containerize the application. But before doing so, there are 3 prerequisites that must be done. First, we need to create and attach an IAM role with enough permissions to allow the VM to communicate with the ECR, since we will be pushing and pulling images to and from the ECR. Then we will install the AWS CLI, and finally we will install Docker. So let us start by creating the IAM role. Here I am in the IAM service. I will create a role. The use case will be EC2, since we will be attaching it to an EC2 machine. I will give it administrator access to make sure I have enough permissions. Finally, I will give it a name and create the role. Now that the role is created, I will proceed to attach it to the machine. Now, I have already installed the AWS CLI and Docker. However, the document attached with this video contains all the steps and commands required to install everything in great detail. So I will validate that the AWS CLI is installed by checking the AWS CLI version. And that Docker is installed using the docker ps command, which lists all the available containers. Evidently, I have no containers over here. There exist several official Docker images curated and hosted on Docker Hub, aiming to serve as starting points for users attempting to use them or build on top of them. Also, there is an official repository for the Apache web server containing all the information necessary to deploy and operate the image. So first, I will start by downloading the image to the server using the docker pull command. I will use the 2.4 Alpine image tag. An image tag is an identifier to distinguish the different image versions available. So after downloading the image successfully, I will list the available images. And as we can see, the HTTPD image with a tag of 2.4 Alpine is now successfully installed on my server. Next, it is time to run a container from this image. The goal is to run the Apache server on port 80 and have it accept requests. So to create a Docker container, I will do so using the docker run command -d, which means run in detached mode or in the background. I will give the container a name, my first container, and I will map the container's port to the host's port so I can actually hit the container from outside the Docker network. And finally, I will use the image and the tag. So now, as we can see, there is a container with the name of my first container and using the HTTPD image running on my machine. Now I need to hit the container using the machine's IP, and hopefully I will get the default Apache page. So there you go, we have the default Apache page loaded as soon as we hit the machine. So now that the base image is successfully deployed and running, it is time to customize it. The official documentation presents clear instructions on the different ways the image can be customized. For example, creating custom virtual hosts, adding static content, adding custom certificates, so on and so forth. So in this example, we need to deploy on the container a custom HTML page. Now, first thing is that I will execute, or I will go inside the container using the exec command. Now I am in the container inside the USR local Apache 2 directory. I will navigate to htdocs, and as you can see, there is an index.html file which contains the default page that gets loaded every time we hit the container. So I need to modify this and add my custom HTML page. First of all, I will add nano. Then I will edit the index file, remove the old content and replace it with my HTML document. Now I will save it, exit the container, and I will perform another request hoping to get the custom HTML page now. So let me get the machine's IP, put it in the browser, and we have the custom HTML application loaded now. Unfortunately, the changes performed will not persist, especially when the container crashes. As a matter of fact, by default, containers are ephemeral, which means that custom data generated during runtime will disappear as soon as the container fails. To verify it, I will simulate a failure in the container by removing it and starting it again. So I will remove the container, I will make sure that it is removed, and I will start another container using the same docker run command. So now I will hit the container again using the machine's IP. And as you can see, the changes performed disappeared. So to persist the changes, a custom image must be built. The custom image is a snapshot of the container after adding the custom website. So I will repeat the steps to add the custom HTML page and ensure that the container is returning the new document again. So let me go back inside the container and repeat the same steps. I will edit the index file, remove the default page and replace it again with the custom document. Exit the container and hit the machine again. Okay. So to create a new image from the customized running container, I will use the docker commit command. Commit my first container. And now I will list all the images available. Clearly, there is a new image with no name and no tag that has been just created using the docker commit command. So now I need to give it a name and a tag, and I can do so using the docker tag command. I will add the image ID, and then I will give it a name, custom HTTPD, and a tag, v1. Now, the image should be created. Yes, it was here created, so now I have a new image called custom HTTPD and has a tag of v1. So What I will do is that I will remove the old container and I will create a new container, but this time using the custom HTTPD image that I just created. So I gave it a new name called my second container, and I am using the new image now. Now if I hit the machine again, I should receive the custom document instead of the default page. So we were able to persist the changes. The custom image is now located on the virtual machine. However, storing the image on the VM alone is not a best practice, especially in real-life scenarios. In fact, this is not a good way to share the image with other developers working on the same image. Also, I have no good or easy way to download and run the image on different servers. And finally, there is a risk of losing the image, especially if the virtual machine crashes and it is not well backed up. So a better solution would be to host the image in a container registry. In this demo, I will be using the AWS ECR to store the image. So first of all, I need to create a container repository. Here I am in the Elastic Container Registry service. I will create a repository that is private. I will give it a name, custom HTTPD. I will leave everything else as default, and I will create a repository. So now, as you can see, AWS created a repository for me with a URI for it, and as you can see, there are no images pushed yet. So the first thing to do is that I need to log into the ECR from my machine, and I will do this using this command. Login succeeded. Now, as you can see here, the repository created on AWS has a different name than the one we created. Therefore, we need to tag the image with the correct name before we are able to push it. So let us do this using the docker tag command. And now, as you can see, I have a third image with a different name now. So I will push the image from the VM to the ECR using the docker push command. So if we take a look here, the image with the image tag v1 is successfully pushed on the ECR. Clearly, we were able to push the image to the AWS ECR. Now to finally test that the new custom image is successfully built and pushed, I will create a third container, but this time from the image located in the container registry. So to do so, I will clean the server from all existing containers and images. Let me first delete all the containers. And all the images. Let's make sure that everything is removed. So I have no containers. Oh, I still have the images. Let's remove them one by one. So no more images and no more containers. Now I will run a third container, but this time I will use the image URI that is from the ECR. So as you can see, docker run -d, name my third container, port mapping, and finally I am using the image from the ECR. So let's try. It is downloading the image, it created a container, and now I will attempt to hit the machine and I hope to receive the custom HTML page. So let's do this. Let's get the machine IP, paste it in the browser, and I have my custom HTML page. Creating images from existing containers is one intuitive way. However, such an approach may prove to be inefficient and inconsistent. In fact, Docker images may need to be built several times a day. Also, a Docker image may require several complex commands to be built. And finally, this approach is difficult to maintain as the number of services and teams grow. Docker files are considered a better alternative, capable of providing more consistency and allowing for automating the build steps. To better understand Docker files, we will containerize the application again, but this time using Docker files. So to do so, the application code and the Docker file must be placed together on the server. Let's do this. I will first create a directory called temp dir. Then I will place the application code inside the directory in a file called index.html. And finally, I will create a Docker file next to the index.html file with the following content. The Docker file has two instructions. First of all, it says use HTTPD 2.4 Alpine as a base image and copy the index.html file from the server to the container inside this directory. So basically, we are automating everything we have done manually before. I will save. And now, to build the image using a Docker file, I will use the docker build command. And I will explain the command after I paste it. So, I am telling Docker that please build, use this Docker file and tag the resultant image with this name. And this dot here is to point to the context or the location of the files. So I will hit enter. And as you can see, it will execute all the commands in the Docker file. And finally, it has built the image and it has tagged it. So if I put Docker images, I can clearly see the resultant image over here with the tag vDockerfile. Now I will push the image to the ECR. Let me get the command. So docker push the image name, and I will navigate again to the ECR, refresh, and the newly created image is over here. Finally, to simulate a fresh installation of the image, I will remove all the containers and the images from the server and will create a final container from the newly pushed image. So first of all, remove all the containers. Remove all the images. I will make sure that there are no containers and no images. And finally, I will run a final version of the container using the custom HTTPD image that I just pushed. And now I will make sure that the container is running. And finally, I will perform a request. And there you go, the custom page that I just created is now loaded. Hi, and welcome to this demo entitled Advanced Docker Concepts. Now that we have learned the basics of containers and Docker, we will take it to the next level in this demo. We will containerize and deploy the NK backend application that we previously deployed on an Ubuntu VM. To do so, we will deploy the containerized version of the Arango database with data persistence, as well as the NK backend service. The following steps will be completed. We're going to first deploy the containerized version of ArangoDB without data persistence. Then we are going to enable data persistence using Docker volumes. Afterwards, we will build the backend service using a Docker file, and we will deploy the containerized version of the backend service. Finally, we are going to perform some API requests to validate the deployment. I have already created the security group with all the inbound rules required and the virtual machine. In addition to that, I installed Docker on the machine. The containerized version of ArangoDB can be found on Docker Hub. I will create an ArangoDB Docker container using the following command. Docker run in detached mode, map the container's port to the host's port. Using environment variables, I am specifying RocksDB as the storage engine and root password to be the password of the root user. Finally, I am using the official ArangoDB Docker image with the tag 3.6.3. Once finished, I will make sure that the image is downloaded on the server and that the container is now running. Using the browser, I will log into the database using the root username and password that we specified, and I will attempt to create some data for testing purposes. So first of all, I will create a test database. Then I will log into it. And I will create a test collection. Save. ArangoDB is now deployed as a Docker container and is able to serve requests on port 8529. However, if the container fails, the data will disappear. To verify this, I will completely remove the container and then I will start the new one with the same command, simulating a total failure. So let us do this. First, I will remove the container. I will make sure that it is completely removed. And now I will start it again using the same command. Now I will log in again to the management console and see what happens. So only the system database exists. All the data that we entered are now missing. On production systems, this is a recipe for disaster. To enable data persistence, I will delete the existing container and recreate it with a named volume mounted to ArangoDB's data directory in the container, which can be found in the var lib ArangoDB3 directory. So first of all, remove the container, make sure that it is removed, and then I will recreate it with the same command, but with the volume, named volume, Arango volume, mounted to the var lib ArangoDB3 directory. So now I will make sure that the container exists and that the volume is created. Now I will go back to the management console and will create some test data. I will enter the root username and password. I will now create a test database, log into it, and create a test collection. Great. Now I will remove the container to simulate a failure, and then I will recreate it using the same command and same volume and see if the data persists. Now the container is created again. I will log back to the management console. Root username and password. And the data persisted. The NK backend service is developed using Node.js and Sales.js. To successfully deploy it on an Ubuntu VM, we had to perform the following steps. Install Node.js on the server, clone the repository, install the dependencies, export the environment variables, and finally start the application. Instead of manually performing all these steps to containerize the service, a better option would be to use a Docker file containing all the commands. So to build the image on the server, first I will clone the repository, and then let's examine the Docker file. We are instructing Docker to use Node.js as base image, set the working directory to /app, add all the files inside the directory to the container inside the /app directory, install the packages, export the environment variables, and finally we specified the run command. Now there are two things to modify over here. First, we have to change the ArangoDB password to the one that we specified in the ArangoDB container. And then the ArangoDB host must be replaced with the machine's public IP. So now I will save, and I will build the image using the docker build command, giving the image a name of backend service and a tag vdockerfile. Now that the build is complete, I will list all the images, and we can clearly see that there is the base image and the final image that was created. Now let's run a container from the backend service image using the docker run command. Let's make sure that the container is up, and let's monitor the logs of the container to make sure that it was able to successfully connect to the database. Great. Now the last step would be to perform some API requests to make sure that the whole flow is working. So I have my Postman collection up and running. First of all, I will hit the health API. I need to get the machine's public IP. I will replace it here on port 80, and it is successfully returning a success message. Now I will attempt to create a person, but first of all I need to modify the environments. And I will send an API request with the following body. A success response is returned, and finally, if we log into the ArangoDB management console, we can see that there is a persons database created by the application, a persons collection, and finally a record.